Okay, so now that we know what atoms are, how can we give energy to an atom? So we've already mentioned chemical reactions. So as the electrons are transferred from one atom to another atom, that can give off energy. We saw an example of that when you take the sodium and you put it into water. Another way of giving energy to an atom is electrically. So by hitting the atom with electricity, you can give energy to that atom. Then you can also give energy to an atom by hitting it with light. So example here of solar cells, solar panels. You can also give energy to an atom by heating it. And so in this case, if you have a piece of ice and you heat it, the atoms start to vibrate and they break apart into individual clumps of atoms. So that's going to be a liquid. And then if you continue to heat it, it breaks apart into individual atoms, and so then it turns into a gas. So then what does an atom do with the energy? So once an atom has received the energy, what can it do with that energy? Well, one is it could make the electrons begin to oscillate. And so that will produce radio waves. Another thing that can happen is that the atoms will begin to move three-dimensionally from that energy. That produces infrared light. Okay, another thing that could happen is the atoms could begin to spin from the energy. That also gives off infrared light. Another thing that could happen is the atom could begin to vibrate, and that produces infrared light. Another thing that could happen is the electrons could jump up and down in their energy levels, the floors of the apartment building. That produces visible light and infrared and some ultraviolet. And then finally, what could happen is that the protons and neutrons could start to jump up and down as well. And that's going to produce X-rays and gamma rays. Now, out of all of that, the one I want you to remember for the exam is, what do the electrons do? The electrons jumping up and down in their energy levels produces visible light. So that's what I want you to get out of this. So let's look at this in a little bit more detail. So here's a picture of the energy levels of a particular apartment building. Now in this picture I've got the spacing the same, but if you look at that picture over there, you'll notice that the spacing is different, that it gets more and more crowded the higher up you go. And that's because the energy levels are not uniformly separated. They have different numbers for their energy levels. Okay, the numbers for the energy levels comes from a particular formula that comes from quantum mechanics, and that's that top formula there, which you don't need to know for the exam. It also has a special unit. So energy is normally in the metric system given by J for joules, but in that thing there, it has a special unit that is called the electron volt. Don't worry about it. It's a very, very small quantity of energy that is associated with what the energy of atoms is. So you don't need to know about that formula. That formula is showing you where the numbers are coming from in that chart over there, which I would give you on the exam. Okay, now the one that's underneath it is very important. So the formula underneath it you should already recognize from a previous lecture, where it was that the energy of light is going to be equal to some constant times the frequency of that light. Now, we don't care about the h. All I want you to see is that the frequency of light determines the energy of the light, or the energy of the light determines the frequency of the light. So that's what I want you to get out of this. So I went ahead and I gave you the Planck's constant here, which you don't need to know for the exam. I just want you to see that the greater the energy that the light gives off, the greater the frequency of the light that's going to be emitted. Okay, let's say that you've got an electron down here on the first floor. We're going to give it energy in the form of electricity, in the form of light. We heat it. So one way or another, we give energy to this electron. It jumps. So the electron will jump to a higher energy level. So maybe it goes up to here. All right, now when it goes up, it absorbs. Say that with me. When it goes up, it's going to absorb energy. When the electron goes back down, it's going to emit energy in the form of light. So when it goes up, it's going to absorb energy. When it comes down, it's going to emit energy. Now you might be saying, but what about if it does this? So what if it jumps so that the electron is located right here? It won't. So according to quantum mechanics, an electron can either be here, or here, or here, or on some other energy level above. It may not be here or here, and it cannot even be right there. You see how close it is to that line? But it's not there. It has to be exactly on one of these energy levels in order to make the jump. If it only has enough energy to get in between the lines, nothing happens. The electron will stay right where it's at. Sounds like a test question, doesn't it? Okay, so here's a sample question. An electron makes a transition from level number 2 to level number 4. Is energy being absorbed or is energy being released? And if so, how much energy? So what we need to do is I would give you that chart on the exam. So you need to find level number 4 and you need to find level number 2. And then you need to find the energy that goes with it. So I have the number of the energy level written on the chart, and I also have the energy of the energy level written on the chart. All you've got to do is subtract two numbers. And always remember, it's final minus initial. Final energy level minus the initial energy level. It says it starts on 4. Well, it's going from level 2 to level 4. Okay, so its final energy level is 4. So it's final minus initial. So we're going to take energy level 4 minus energy level 2. Keep in mind those numbers have negative signs on them. So you're subtracting two negative numbers, and so that's the reason why it turns out to be positive 2.6. And then the unit is the electron volt. So that's just the unit that pops out of the formula. Okay, now it's going from 2 to 4. So it's going from here up to here. It's going up. So that must mean it's absorbing the energy. Okay, so real atoms have multiple electrons, and each of those electrons can be doing different kinds of jumps. And so each jump is going to produce a particular amount of energy, and then each energy corresponds to a different color of light, a different frequency of light. So that when you take an element or an atom and you heat it up or you hit it with electricity, there's going to be multiple electrons jumping up and down, producing different colors of light. So in this picture here, you see that black bar with only certain colors of light on it. Those are the allowed jumps for the electron. What's the black part? So the black part represents the forbidden jumps. That would be like jumping from here to here. You can't produce a color, so that's why it looks black in certain parts of that spectrum. So we're going to call this an emission spectrum. Okay, now how do we observe a emission spectrum? So you're going to do that, or you may have already done it in lab. And the idea is you're going to have a glass tube that has a certain gas in it. You take the glass tube, you put it into a machine that hits it with electricity. The electricity makes the electrons jump up and down so that it starts to emit the various colors associated with that particular gas. Okay, but we need to separate the individual colors. So all of those individual colors are blended together to give you the color that you're seeing coming out of that electrical device. So the device that we use to spread the light out into its individual colors is, we could use a prism, a piece of glass. But another thing that can do it is called a diffraction grating. And so a diffraction grating is going to be a piece of plastic that has multiple lines scratched into it. And then those lines act like a picket fence so that when the light goes through those lines, it causes it to spread out. That was the definition of diffraction. So that's why this thing is called a diffraction grating. So the point is, the light goes through it, it's spread out, and then you can see all the colors that were contained in that particular spectrum. So here's some typical spectrums for different kinds of elements, and you see that each element has its own unique spectrum of colors. It's like a fingerprint, so that we can look at the light that comes from a star, and then as we put a diffraction grating on our telescope, then we look at all the different colors produced by that star, and with a computer we can separate all of those different colors to figure out what were the elements that were inside of that star. Pretty impressive. Okay, and then this one just shows you that every element in the periodic table has its own unique set of colors that goes with it. Okay, and then I did want to show you that certain kinds of jumps in the apartment building produce visible light, but you can have other jumps. And so some of the other jumps in the apartment building also produce ultraviolet light and infrared light. Don't worry about it. Okay, let's take a break, and when we come back, we will talk about two other kinds of spectrums.